This section is going to cover a really powerful aspect of natural language processing, and that's classifying text using your own custom labels to create a custom classifier. This is a supervised machine learning problem using different classification algorithms. The algorithms we'll be using for the lessons in this section are logistic regression, naive Bayes, and linear support vector machine. We won't be covering in too much detail how these algorithms work. We'll just be using them for text data. But if you're interested in learning more about these algorithms or how to tune specific hyperparameters, get started building our own custom text classifier using logistic regression.
Even though it's called regression, logistic regression is actually a classification algorithm. This means that its goal is to predict categories, also called classes. An example for such prediction can be whether a student will pass or fail an exam. This is different from regression algorithms, where the objective is to predict a continuous value like someone's exact exam score. Logistic regression is a strong starting point when building a text classifier. You can use it on its own or as a baseline model to compare against more complex approaches later. Let's begin by building a logistic regression model to classify our text data. To get started, we need to import a few Python packages. First, pandas will help us handle and organize the data. Then, from scikit-learn, we'll import only the specific tools we need: count vectorizer, train test split, logistic regression, accuracy score, and classification report. For this exercise, we'll use a sample dataset of sentences paired with their sentiment labels. Each sentence is marked as either positive or negative. Our goal is to build an algorithm that can learn from this data and then classify new sentences by their sentiment. As you've seen in earlier lessons, there are already many pre-trained sentiment analysis models available. However, sometimes their accuracy may not be high enough for your use case, or you might have very specific data that doesn't work well with existing models. In those cases, building your own custom model is a great solution. So let's do that. Here, we're creating a pandas data frame with two columns: text, which is the actual sentence, and sentiment, which is the label, either positive or negative. This dataset will serve as the training ground for our logistic regression model. The next step is to shuffle the dataset. This makes sure we have a good mix of positive and negative sentences throughout, instead of having all the positives grouped first and all the negatives grouped later. For this purpose, we'll use the sample function from pandas with the fraction set to 1. Setting frac equals 1 means we're taking 100% of the data, but in a randomized order. After shuffling, we reset the index so the rows are numbered neatly again. The argument drop equals true tells pandas not to keep the old index as a separate column. Next, we prepare the inputs for our algorithm. X will hold the text data, the text column. Y will hold the target labels, the sentiment column. The next step is text vectorization. As you remember, this means converting our sentences into numbers so the machine learning model can work with them. Here, we'll use the bag of words approach with scikit-learn's count vectorizer function. So each word in our dataset becomes a column. Each sentence is represented as a row, and the values show how many times each word appears in that sentence. That said, although we're using bag of words here, feel free to experiment with other methods we covered earlier, such as TF-IDF vectorization. Okay, we'll start by creating a count vectorizer object that we'll call countVec. Then we run fit transform on our X data, which both learns the vocabulary and transforms the sentences into numbers. We'll call this result CountVec fit. Finally, we'll convert the bag of words matrix into a pandas data frame. For the column names, we use getFeatureNamesOut, which returns the words from our vocabulary. Printing the data frame shows us the bag of words representation. Each row corresponds to a sentence. Each column corresponds to a word. Now that we've turned our text into numbers, the next step is to split the data into training and testing sets. This is a key step in machine learning. The training set is the portion of data the model uses to learn. The testing set is kept aside until the end. It helps us check how well the model performs on data it hasn't seen before. When we split the data, we separate it into features, the input data, and labels, the answers we want the model to learn. Features, in our case, the bag of word sentences. Labels, the sentiment for each sentence, either positive or negative. That's why we create 4 variables: xtrain, which are the training features or sentences in bag of words form; xtest, which are the testing features; ytrain, which are the training labels or sentiment values; and ytest, which are the testing labels. We set test size equals 0.3, which means 30% of the data is used for testing and 70% for training. A split like this gives the model enough data to learn from, while still leaving a significant portion aside to evaluate performance. And you'll often see test sizes between 20% and 30% in practice. We also add random state equals 7, so the split is reproducible. We'll always get the same train test split each time we run the code. With this setup, xtrain and ytrain will be used to train the logistic regression model, while xtest and ytest will help us evaluate its accuracy. Good. Now it's time to train our logistic regression model. We'll call it LR and create it using the logistic regression function. Next, we train the model with the fit method. The fit method takes in our training data and teaches the model to find patterns. It looks at the bag of words features in xtrain and learns how they are linked to the correct labels in ytrain. Next, we want to see how well our model does on data it hasn't seen before. This is where the testing set comes in. We use the predict method on xtest to generate predictions. Then we save these results in a variable called ypredLR. Okay, let's now measure the performance of the model. The first metric we'll check is accuracy. Accuracy tells us the percentage of sentences the model predicted correctly. To calculate this, we compare the true labels with the predicted labels. We can see our model isn't performing well. However, as mentioned, this is a really good baseline model to use before you move on to anything more complex. Finally, we'll print a classification report. This gives us more detail than accuracy alone. It shows how the model performed for each class, positive and negative. The report includes some additional metrics. Precision. Out of all the sentences the model predicted as positive or negative, what proportion were actually correct? Recall. Out of all the sentences that were truly positive or negative, what proportion did the model correctly find? F1 score, a single number that combines precision and recall into one measure, balancing the two. At this stage, don't worry if the results are rather low. That's expected because we're only using a very simple baseline model. The goal here is to have a starting point. Later, we'll try more advanced methods to improve these results. Let's try to improve the low accuracy score from the previous lesson by using naive Bayes. Naive Bayes is a simple classification algorithm that works using probabilities. For example, if we want to separate positive from negative reviews, naive Bayes looks at how often certain words appear in each group. Then it uses these counts to estimate the probability that a new review belongs to each group. Each word acts like a clue. Words such as great or amazing point toward the positive class, while words like boring or terrible point toward the negative class. Naive Bayes collects all of these clues, combines them mathematically, and then predicts the most likely class. It's called naive because the algorithm assumes each word in a review is independent of the others. That's not always true in real life, but this method still works surprisingly well for many text-related tasks, such as spam detection or sentiment analysis. Okay, to begin, let's import the multinomial naive Bayes classifier from the scikit-learn library. Next, we create our algorithm instance and call it NB. We instantiate it using the multinomial NB constructor with empty brackets. We then train the model by calling the fit method and inputting our training data xtrain and ytrain directly in the same line of code. After training, we create predictions on our test dataset by using the predict method from sklearn. We then compute the accuracy score by comparing our predicted labels yPredicted_NB against the true labels yTest. We can see here the accuracy has improved slightly, however, it still has not worked very well. The naive Bayes model shows some improvement as it can classify both positive and negative classes. However, there is still room for improvement. We can try one more model to see if we can push this accuracy further. The last algorithm we'll test is called a linear support vector machine, or linear SVM for short. The main idea behind this algorithm is to find the best possible boundary that separates the classes, in our case positive and negative sentences. When we have only two features, this boundary is a straight line on a 2D graph. The algorithm tries to place that line so that the distance between the line and the closest points from each class is as large as possible. These closest points are called support vectors, and they are what define the position of the boundary. If our data has more than two features, which it usually does, the same logic still applies. Instead of a straight line, the boundary becomes a flat surface, like a plane, or even a hyperplane in higher dimensions. But in simple terms, the SVM always tries to find the best possible straight separation between classes, no matter how many features the data has. Linear SVMs are especially effective for text, so they're a strong choice for sentiment analysis. Let's try it out. The first step is to import the package we need. From sklearn.linearmodel, we import sgd classifier. There are a few different classes in scikit-learn that can run a linear SVM. We'll use this one in our lesson. If you look at other tutorials, you might see a different class name, but under the hood, they are all applying the same algorithm. Next, we create our model and train it on the data. We start by instantiating the SGD classifier class. We then call the fit method on our training data. As usual, this will teach the model to recognize patterns in X-train and the correct labels in Y-train. After training, we create predictions and store them in YPred SVM. We use the predict method of the SVM model on our X-test dataset to generate these predictions. Let's now calculate the accuracy score to see if we have improved from other models used previously in these lessons. We are still getting a result that is not that great. What can we do about it? Well, we might need to revisit our data, clean it up further, or add more data to try and improve the accuracy score. This is a common scenario in machine learning projects. You do not always get the best outcome on the first try. It is necessary to run the models, evaluate their performance, and then potentially go back to your data or problem formulation to make changes upstream in your workflow to increase accuracy. In the upcoming lessons, we will cover a full practical example where we will revisit these algorithms and try them out on a different dataset. See you soon.